this is everything we will be doing up until the next exam in this topic. Pretty large topic. I want to start out with some with some background on some math techniques and probability, just so that you can get just to make sure that everybody's aware of some of the background, so I don't make any assumptions about your knowledge and some of the mathematics that I'll be talking about. For probability and statistics, I very much find that this is one of the best books that I've run across, is Hines, Montgomery, Bolton, and Bohr, The Probability and Statistics in Engineering. The problem with it is that it has calculus in it. And so if you have calculus phobia, that might not be the best place to start. But it's very good. The Walters Statistical Tools of Safety Management is sort of the opposite end. It is like a recipe book. It takes you through things step by step by step. The trouble is, he doesn't have a lot of things in it. But I do draw from it, from quite a few of these when he does have it available. And then Rowland and Moriarty have probability distributions and probability techniques. The trouble is that it's almost like shorthand. They have it presented so briefly that they skip about 1 million steps between the beginning and the end, and it's one of those books that when you're reading it, it says, and it should be obvious that the result is, and it's not obvious at all. You have to go, when I was reading that the first time, I went to about 3 or 4 other books to try to figure out how they got from point A to point B, because they weren't going to explain it. That's why I said it's not a very user-friendly book. That's probably why it's not in print anymore. And then the Hogan, Tanis, and Levine, Ramsey, and Schmidt are also pretty good ones. But like I said, I think this one is by far the best. The Evans, Hastie, and Peacock is more of a reference. It has every probability distribution that you can think of. There's probably about 30 or 40 of them in there, and it's in a reference book type of arrangement. And it's in alphabetical order, and you flip through it. There's about 3 or 4 page summary, each one of the probability distributions. Peacock was in our department for a while. He told me this is the most boring book ever written. Well, if you sit down and try to read it, yes, it puts you to sleep in about 30 seconds. But it's a good reference book. So that's, for what it's worth, that's my assessment. Now, like I said, for some reason, summation and product science seem to be a constant thorn in the side of everybody, so I thought I'd just briefly go over them again. Remember summation sign. What you're doing is repeating the operation inside the sign from the lower range for I to the upper range of n. So this one, if I expanded it and took away the summation sign, this would be for I equal 1, 2, 3, and 4. Okay? So whatever x1, x2, x3, and x4 are, you substitute those values in, and here I just arbitrarily gave values for x1, x2, x3, and x4, and that's what you end up with, 9/5. Okay? Just add it together. Summation, think of addition of all the components. Now, another thing that is virtually the same thing, but it's called product sign, and it uses a capital pi instead of a capital sigma. And you have the lower limit and the upper limit, except instead of adding the operation inside the function, you multiply them. So this is 1 over x1 times 1 over x2 times 1 over x3 times 1 over x4. And it gives you a substantially different answer, obviously. 9/5 versus 1 over 100. This one we're going to use pretty extensively in system in network reliability. We use the product sign quite a bit. So, questions on that? All right. I'm just going to tear along until somebody throws something at me. Factorials. Another thing that seems to cause a lot of wailing and gnashing of teeth. And I talked about this a lot in QM last semester, but it's anything with that sign, you just multiply that number times everything less than it down to 1. And that's a factorial. Now, this is an example of how to reduce it so that you don't make your calculator cough. If you have something that's really large, like 100 factorial, at least at one time, calculators didn't do 100 factorial. Maybe now they do. Do your calculators cough at 100 factorial? Or can they do it? Somebody test your calculator and see whether it does 100 factorial. Error, yeah. So, since it's very likely that 100 factorial might appear, and you wanted to do, for instance, combinations, 100, let's say I gave you something like this, that you got this number, 100 objects taken 5 at a time, right? That combination. Remember that's n objects, x is the usual nomenclature. So this would be n factorial, x factorial, n minus x factorial. So that would be 100 factorial, it comes out to that, 5 factorial, and 95 factorial. Okay. Oh, actually, no, that's something else. But let's say I gave you that. Okay. And your calculator coughs at 100, so what you end up doing is 100 times 99 times 98 times 97 times 96 times 95 factorial over 95 factorial and 5 factorial. Cross those out, now you can do it a lot more easily. And you might even be able to, let's see, 5 times 4, let's see, take that 5 times 4 times 3 times 2 times 1. 5 times 4 is 20, so that becomes 5. And let's see, 2 and 98, so that becomes 49. And 3 into 99 becomes 33. That's a lot easier. So that's the way you should think about if you are presented with a factorial that you really can't do. By brute force, you have to do it with a little more finesse like that. So it's a good idea to learn how to do that, or to think about it that way. Does everybody see what I did there, right? Or if you don't, please tell me. Okay.
Well, my calculator will only get a 69.
It only goes up to 69. Interesting. Okay. What is 69
my phone
factorial?
did it.
Just out of curiosity. How many to the power of what is really the order of magnitude?
98.
To the power of 98. Okay, so it won't go over probably 99 to the power of 99. Okay.
My phone did it.
Sorry.
My phone did it.
Oh, it did. That's why you can't use a phone. There are actually other reasons, but
The TI-89 will do it too.
oh, will it?
Listen, it's $12 at Walmart. Yeah, it's trying to buy good much.
And unless I ask you to show your work, you're in good shape. So anyway, that's factorial, summation sign, product sign. Now logs. Okay, if you've been through human factors, this should look agonizingly familiar. If not, let's talk about it again. Logarithm, remember, is the power that you have to take a number 2 to get whatever the operand is. Do I have it here? No. So let's we think in common logarithms. We think in base 10. So a common log, which on your calculator is just log, which is really base 10 logarithm. So a log of 10 equals 1, because 10 to the first equals 10. Okay? A log of 100 equals 2, because 10 to the 10 squared equals 100. Log of 1,000 equals 3, because 10 to the third equals 1,000, and so on. Okay? Now, and I can't do this in my head, but The other thing that's on your calculator is the natural logarithm, right? That's log base e. And e is 2.718. It's an irrational number like pi. It goes on into infinity, okay, without repeating. And it's, I can't remember the formula for it, but it's a series, an infinite series. And it was developed for econometric reasons, purposes, but we use it now constantly. Base E is constantly used in scientific applications. So, and it's called natural logarithms, and it's abbreviated LN. It's on just about every calculator. Okay. So, natural log of E equals 1, because e to the first equals e. Natural log of e squared, whatever that is 2, because e to the second equals e squared. And that is 2.718 squared, etc. Now, your calculator only has common logarithms, base 10, and natural logarithms, base e. Now, it's very frequently you need to find the base 2 logarithms, for instance. It's a common requirement if you're working with reliability, for instance, or with decisions, because you're making binary decisions. You have to find base 2. Since base 2 logarithms aren't on your calculator, you can either use it, find the base 2 logarithm using base 10, or you can find the base 2 logarithm using the natural log. In which case, you want to find the log base 2 of some number. You just find the log base 10 of that number and divide it by the log base 10 of 2. Or log base 2 of some number, you find the natural log of that number and divide it by the log base 2, natural log of 2. Okay? So you can find base anything by just dividing it by the logarithm of 2, whatever log you're working with. So far, so good? You're just bored out of your minds? So anyway, that's the logarithms that I wanted to make sure everybody was aware of. And then combinations and permutations. In the binomial, we use combinations. It's this. Okay? The difference between, and for contrast, we're not going to do permutations very much. But by contrast, there are always more permutations than there are combinations. Because in combinations, the order doesn't make any difference. In permutations, order does make a difference. So AB and BA is a different permutation, even though it's the same combination. Okay? And the way you can remember that is that the denominator in combinations includes x factorial, where it doesn't in permutations, and since the denominator is bigger, that means that you will have fewer combinations. So that's the difference between a combination and a permutation. And like I said, that's for contrast, because this is what we're really interested in, is combinations. And rarely are we interested in permutations and probability. I am including in the general introduction to the field of probability some set theory, because it involves aspects of probability. And so you've probably all seen in one form or another Venn diagrams, okay, where you have the universe, and this is the universe as we've defined it, usually within the outer box. The universe is defined as lowercase omega, it's not W. Okay? Please don't call it W. Drives me nuts. Every semester somebody calls it a W. It's a lowercase omega, and then you have sets within the universe. Here we happen to have 3 sets, A, B, and C. A and B happen to intersect, so that means that A and B have some elements in common, whereas C does not intersect with either A and B, so there are no common elements in common with either one. These are sets of events. It's a typo I just realized. recognize sets of events within the universe, and they may or may not overlap or intersect. Now, the way that we mathematically depict intersection and union is intersection is, and we'll talk about a little bit about Boolean mathematics later, but that's a Boolean and, okay, because we'll be talking about in fault tree analysis, there's and or gates, okay, and this refers to the same thing as an and or gate in a fault tree. So an intersection of two sets, in this case I happen to have chosen A and B, is an inverted U. That's the symbol for an intersection in set theory. And the way it can be defined in two different ways. It can be defined as the probability of A given that I'm in B. Okay, in other words, I know that I'm in B, which is this circle right here. What's the probability of also being in A? Okay, this is a conditional statement right here. Okay, so it's given that you know that you're in set B, what's the probability of being also in set A? And then times the straight probability of being in set B. The intersection of the two is also defined as the converse of that. The probability of being in B given that I know that I'm in set A. In other words, I know that I'm in set A, what's the probability of being in set B also? Times the probability of A. And I'll give you an example later, but just think about it for now. Okay, so those are two ways to define intersection. Union, and so what the intersection is, as it implies, the intersection of A and B is this area right here. It's the part that they have in common. Okay. The union of A and B, and that's a Boolean or, is a U. Okay. That's the symbol for the union. And what that means is that I have to take everything that's in A and everything that's in B. Now notice, think about the logic of this. If I take A and add it to B, I'm double counting what's here, right? So that's why you have to subtract the intersection. So it's the probability of A plus the probability of B minus the intersection of A and B. Okay? I have to subtract that or else I double count it. And then I can substitute that intersection either this formula or this formula, depending on the data that I have available to me. Okay? So far, so good? Now, what about the intersection or the union of A and C? The union of A and C won't be zero. It's just the probability of A plus the probability of B, because I have no intersection. Intersection is zero, but union is just the probability of A plus the probability of C. And for completeness, you can subtract off the intersection, but the intersection is null. There are laws for union and intersection. I won't dwell on these either, but just so you know, A union B is the same as B union A. A intersect B is the same as B intersect A. There's associative laws that apply. I can group them in any way that I want, and it will still be valid. I can either find A union B and then take the result and take the union with C, or I can take B union C and take the result and get the union with A, and it gives you the same result. Likewise with intersection. And then distributive laws also apply. It's very handy. A union B intersect C is the same as A union B intersect, because see here I'm taking, these are only unions, these are only intersections. Here if I take the union of an intersection, I can take the union of each of those components and the intersection of the two, and it will give you the same result. These are just handy things to know when we're working with union and intersection. Okay, let's take a look at. I'm not quite to my example. The probability of the universe, the way we define everything, all of our sets plus everything that's outside of all of our sets is 1. And by definition, if it's in the universe, there's probability of 1 that one of our events is going to be in our universe. the probability of the null set, in other words, of not being anything, is 0. Anything in union with the universe, either A, B, or C, in union with the universe, has a probability of 1. I combine it with the universe, it's going to be everything. If I take anything in intersection with the universe, it will be itself. So A intersect with the universe is A, B intersect with the universe is B, and C intersect with the universe is C. If I take anything in union with itself, it's just probability of that set. Anything in intersection with itself is the probability of that set. Right? Those are just some identities to keep in mind. Does everybody understand each one of those, how we get those results? Okay. So let's take an example with some numbers in it. Probably should bring in some colors next time. But let's say that our universe consists of 120 items. And that there are 20 items in A, and that there are 30 items in B, and there are 10 items in C. Right? So that means that there's things out here, right? Because I have only 60 things that are inside of a set. Yeah, 60. There's 20 here, 30 here, and 10 here. 60 items that are inside of some set. And there's another 60 that are out here, outside of any of the sets. So that means that the probability, these are the raw numbers. So the probability of being in the universe, of course, is 1. The probability of A, of being in A, is 20 out of 120, right? Because there's 20 items in A, and there's 120 total. B is 30 out of 120, and the probability of C is 10 out of 120. Okay, I'm converting these numbers into probabilities. And remember, probability always has to be a number between 0 and 1, right? Can't be more than 1, can't be less than 0. Now, I know that A intersect B has 5. Okay, so in here, there are 5 that are common to both A and B. Okay, A intersect C is the null set, and B intersect C is the null set. You can see that by looking at it, but just by definition. So that means that A intersect B is 5 out of 120. 5 of those out of 120. So I know that intersection, the probability of that intersection. So going from there then, we can calculate some other intersections and unions that may be of interest. So, I want to know what's the probability of A given that I'm in B. Now I'm doing this redundantly so that you get an intuitive feel for what this means. Okay, I know that I'm in B. What's the probability of being, also being in A? Okay, well, we can look at this and say 5 out of 30 is my result, and that's the simple way to do it. 0.168, 5 out of 30. However, let's apply our formula, because remember the intersection is probability of A intersect B is equal to either probability of A given the probability of B times the probability of B, or it's equal to the probability of B given A times the probability of A. Right? So I see that I have, if I manipulate this a little bit, that I can take this top formula and convert it to that. All I did was divide through by the probability of B. And I got the probability of A intersect B over the probability of B. And from the results on the previous page, I get exactly the same result. Just to give you an intuitive sense of what that means. The probability of that intersection, or the probability of that conditional probability, sorry. And if we take the bottom one here and do the same thing with it, probability of B given A, it's the same thing. Given that I'm in A, it's 5 over 20 or 0.25. I can do the same manipulation, A intersect B over the probability of A, from the previous page's results, and you get the same result. Now, I might not have these handy numbers available, in which case I would have to use this result, these results right here, to get that conditional probability. So now what I can do is I can find all of the unions, because I already found the intersections, and I found the conditional probabilities. Now I can find the union. So probability of A union B, A, B, and A intersect B, A union C, A, C, A intersect C, and B union C is B and C, and B intersect C. These two intersections are 0, and this intersection we found in the previous page result. So that's basic set theory, and we can take that and apply it to a slightly more complicated problem, and that becomes Bayes' theorem now. Let's say that our universe is divided up into sections. We'll call those sections B1, B2, B3, and B4. And then I have a subset that intersects with at least 2 of those sections. Okay. Now, what you can see just by inspection, you can see that the probability of A, this subset in here, and I happen to have it intersecting all 4 of the sections of the universe, is A intersect B1, A intersect B2, A intersect B3, A intersect B4. It's simply the addition of those 4 intersections. Right? So, I know from this result right here that A intersect any B, 1, 2, 3, or 4, I'll just call it B sub I, is either A given B sub I times the probability of B sub I, or the probability of B sub I given A times the probability of A. Okay. What we can do then is, let's just use this part of the result right here. Forget about this one for the time being. So let's say probability of A intersect B sub I equals the probability of B sub I given A times the probability of A. Rearrange it so that I isolate B sub I, the probability of B sub I given A, and I have A intersect B sub I in the numerator and the probability of A in the denominator. Now, A intersect B sub I already know is equal to this guy right here. Right? A given B sub I times the probability of B sub I. And I know that the probability of A from this is the summation, or I'm sorry, not from this, from probability of A. Oh, actually, yeah, if we take each one of these intersections here and substitute for each one of these, the probability of A given B sub I, B sub 1 times the probability of B sub 1, and this is the probability of A given B sub 2 times the probability of B sub 2, and so on for B3 and B4. That can be written shorthand by the summation, probability of A given B sub I, summation of I equals 1 to n, in this case n is 4, times the probability of B sub I. So by manipulating these 2 relationships, we can take this conditional probability and reduce it to either one of these 2 equations. Right? That relationship is called part. Bayes' theorem goes way beyond this, but that's part of Bayes' theorem, is the relationship between this subset and each one of these sections of the universe, and how those probabilities are related. So let's take a look at an example that hopefully will make it a little bit more concrete. Let's say that we have 3 machines, and we know that the section or the amount of output that comes from each machine. So our universe consists of the output of those 3 machines. So that means that the probability of M1 is 0.35 because it produces 35%. M2 is 0.25 because it produces 25%, and M3 is 0.4 because it produces 40%. They add up to 100% of our production. Okay. I can track by I can observe the defects that result from each one of our machines. Machine 1 has a defect rate of 2%, and that results in a probability of 0.02. Machine 2 has a defect rate of 1%. Machine 3 has a defect rate of 3%. Notice I resisted calling it 1%, 2%, 3%, although that's what I started out with until I realized what I was doing. So now we have conditional probabilities. Defect given we know we're on machine 1, a defect given we know we're on machine 2, and a defect given that we know we're talking about machine 3. So now we have conditional probabilities for defects, and you can think of defects as this subset. Okay, there's a subset of machine 1, machine 2, and machine 3 that have defects, and that's from our whole universe. A question we can ask is what's the probability of defect overall? Because we have it for each one of the machines, but we don't have it for our entire output. So, remember that we had a relationship with the probability of A equals the summation for I equals 1 to n, however many subsets there are, of the probability of A given B sub I times the probability of B sub I, probability of A, sorry. Let me make sure I got that right. Right. Okay, because what we're looking at is this relationship right here. B sub I, that's what I thought. Or, conversely, is the probability of B sub I given A times the probability of A, because what we're using is this relationship right here. Right? So there's two ways to get at the probability of A. In this case, because the probability of A is actually these series of intersections, which we can arrive at through one of 2 different methods. Okay. So, keeping that in mind, and also keeping this relationship in mind here, that the probability of B sub I given A is equal to the probability of the A intersect B sub I over the probability of A, and that's also equal to the probability of, let me make sure I get it right, B sub I, that's probability of B sub I over the summation, and I'll just leave the limits off. It's probability of A given. Seems to me like I'm missing something, but I'm not sure what it is. A given B sub I. Probability of B sub I. Okay. So this is, if I want to find an individual conditional probability, I can find this conditional probability, which is the converse of that, over the summation of all the conditional probabilities. So we go back to our defects. This is the probability of a defect, is the probability of defect given each of the machines, which we know, we've collected the data on it, and we know what the probability of coming from that machine is, because we know the portion of the output that comes from each one of those machines. So if I take the sum of each one of those, you can get the overall defect rate, okay, which is essentially coming from this result right here. Because A is defects, okay, because that's our subset right here, and the probability of each one of the sections is the same as our probability of the machine. Okay. And what you can end up doing is that will equal to the probability of defect equals, first of all, the defect given machine 1, which is 0.02, times the probability of being on machine 1, which is 0.35, plus the probability of a defect given machine 2, which is 0.01, times the probability of coming from machine 2, which is 0.25, plus the probability of a defect given machine 3, which is 0.03, times the probability of coming from machine 3, which is 0.4. And then when you go through all that arithmetic, you get the result, which was 0.02, I think? 0.0215. So the overall defect rate for the company, or for the factory is about 21%, 21.5%.
No, 2.1%.
Oh yeah, 2.1. I wrote it down wrong. 2.1%. Thank you. Yeah. Maybe. So then what I can do is work backwards. So I can find out, if I have a defect, what's the probability that that defect came from machine 1, or machine 2, or machine 3? Okay. And that's a slightly different question, because now I'm already in the set of defects. I'm already down here. Okay, and I want to know what's the probability that it came from each one of these machines. And that's phrased slightly differently than what's the defect rate for machine 1, and the defect rate for machine 2, and so on. So now we're using, again, we're using this result right here. Probability of a defect, which is A, given that it came from machine 1, and I am taking the defect rate as a denominator actually what I'm doing is I'm using this equivalent right here. Because we know that that's equivalent, they're both equal to the probability of a defect. And I have already calculated, I already know the probability of defect given machine 1. So I know this, and I know what the probability is coming from machine 1. I know what the probability, overall probability of a defect is, which is this right here, which is right here. And so I have everything except this component right here, right? And you do the manipulate it so that you take this and divide it by the probability of defect, which is exactly what I did right there, and you can get the probability that it came from machine 1, given that it's a defect, machine 2, given that it's a defect, and machine 3, given that it's a defect. Does everybody see, or each one of these, do you want me to put the numbers to this? Would that make it easier?
Yes.
Yes, okay. Okay, so the probability of machine 1, we already know was 0.35, right? The probability of the defect, given that we're on machine 1, we already know is 0.02, right, for machine 1. So it's 0.02 times 0.02, okay? And then we divide by the overall probability of defect, which we just calculated at 0.0215. I get that 0 in there, it's important. And that gives us the probability that that if we have a defect, the probability that it's coming from machine 1. And if we have a defect, the probability that it's coming from machine 2, it's the probability of machine 2, which is 0.25, times the probability that it's given that it's machine 2, that it's a defect, is 0.01 over the overall probability that it's a defect, which once again is 0.0215. Okay, and then finally for machine 3, it's 0.4. Probability that it comes, that if it's from machine 3, the probability of the defect is 0.03. And again, 0.0215. Okay? So this is a useful application of Bayes' theorem. It's one of the many applications, but this is a useful one. And I think that I came up with some safety-like problems that you could apply this to. But it's like I said, there's a lot more applications of Bayes' theorem, but this is a useful one for our purposes. All right, let's do some more probability background then. Like I said, probability, any value between 0 and 1, and if you multiply it by 100, you get a percentage. People tend to think in percentages. I was talking to a group at Human Proving Grounds, and for some reason, that must have touched a nerve. That made them so incredibly angry. I couldn't even talk to them after that. But I'm not quite sure. I still wasn't quite sure why that made them so angry. That if you multiply probability times 100, you get a percentage. But apparently they had some sort of internal squabble about that, and I just tended to touch on it. But we tend to think in percentages. What's your chance of tossing a head? It's 50%. Okay? That's the way we think, and that's 100th of a probability. Okay? So, an experiment then is some activity that we perform where we have a number of different outcomes. And the sample space, and the activities can be things like coin toss. I'll be talking a lot about coins and die, just because that's something that's easy to think about, and we know what the outcome is going to be. Fair coin, fair tie, die toss. Sending a shuttle into orbit is an experiment because there's a number of different outcomes. There's a sample space, I don't know and there's a probability of what will happen. Performing a task, it's an experiment. You can either fail, not fail, or possibly, depending on how you define it, have something in between. So the sample space is everything, you're enumerating everything that can happen, as far as you know, and assigning probabilities to it. And each one of those outcomes is called an event, a single event in the sample space. Now, something simple like a coin toss, barring the twilight zone where it lands on the edge, you essentially have two possible outcomes, heads or tails. Okay? And your sample space then is heads or tails, so the outcome of an experiment of a coin toss. A toss of a die, if it's fair and six-sided, is 1, 2, 3, 4, 5, or 6. Those are 6 events, and the sample space is a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so whatever we are going to talk about, we will talk about in terms of the sample space, the way we define it, and what each of those events are in the sample space. A couple of laws. The first one is the addition law, that the way we have defined our events, if we take all of the events in the sample space and add the probabilities of each one of those events, they should add up to 1. Otherwise, we've made a mistake. Okay? Otherwise, we missed one of the events that we should have accounted for. Okay? Or you can also take a subset of them. And the probability of rolling a 2 or a 6, if I have a fair die, is 1/6 plus 1/6, right? And the probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6 is 1/6 plus 1/6 plus 1/6. Add it up 6 times and you get 1. So that's this is the addition law for probability. Okay, and if you'll notice, I always put if it's a Boolean and or Boolean or. Okay, if I get a 1 or a 2, that means the probability of a 1 or a 2 is 1/6 plus 1/6. And that's a Boolean or. Okay. Now, if it's a Boolean and, the probability is, we usually talk about things in succession. The probability of me rolling a 1 twice in a row is 1/6 times 1/6, if it's a fair die. The probability of me rolling, getting a heads on two subsequent rolls, or two subsequent tosses of the coin, is 0.5 times 0.5 or 0.25, because there's 4 different outcomes for 2 tosses of coin: heads and tails, tails and heads, heads and heads, tails and tails. And there's 0.25 probability of each sequence. Right? So that is a Boolean and, a 1 and a 2, a head and a head. And the complementary law is sort of the complement of the addition law, and that's the one that I always use on the quantitative methods exam, the first one, where I talk about what's the probability of rolling at least or probability of getting no mistakes, or at least 1 mistake, okay? Because the probability of doing, let's see if I have a probability of failure, you remember this, of 0.25, whatever, doesn't matter. And I do something 10 times, so n equals 10, what's the probability of getting at least 1 mistake? Okay? Probability of getting at least 1 mistake is 1 minus the probability of getting 0 mistakes, right? You can either do it the hard way and do probability of 1 mistake, plus the probability of 2 mistakes, plus the probability of 3 mistakes, plus the probability of 4 mistakes, all the way up to 10, or you can just calculate the probability of 0 mistakes and subtract it from 1. That's the complementary law. what we will spend the rest of this topic talking about is probability distributions. Probability distributions are ways of assigning probabilities between 0 and 1 to events that occur. Probability distributions are not, as I was saying this during the break, they're not abstractions. Probability distributions are ways, are attempts to define things that occur in nature. Okay? Let's take the normal distribution. I won't talk too much about the normal distribution because we do that a lot in quantitative methods, and we also will do it ad nauseum in human factors. But let's talk about the normal distribution. If I take enough people and I measure their height, or their weight, or the length of their forearm, or the length of their middle finger, or the length of their big toe, or if I go out to the trees out here and I take a species of tree and I measure the length of the leaves on that tree, if I get enough of them, it will look like a bell curve. It will always be distributed like that, where you have a cluster, greatest number at the mean, and then as it gets very small or very large, there's diminishing probability. That's a description of a naturally occurring process. There are other distributions that measure other things. The decay of carbon in carbon-14 is an exponential distribution. It decays a lot at the beginning, and then it levels off. Any radioactive decay actually behaves that way. Inter-arrival times, it's less obvious, but if you go to a line and watch a line at a bank or at a restaurant, anywhere where you have lines, what happens? It grows and it shrinks. Grows and it shrinks. So when it's growing, the times between arrivals are very short. That's why you have this cluster down here. And as it shrinks, the times between arrivals get very long. But there's not many of them. Okay? Then there's a whole bunch of them that arrive in short inter-arrival times, and then they get longer. That describes the shrinking and growing of a line. That's an exponential distribution. We'll be talking about that. All of the distributions describe things that occur. Okay? They're not abstractions. That's why there's so many of them, because you can't take one distribution and apply it to everything, because it doesn't work that way. Different distributions apply to different natural occurrences. Okay? So, and then there's another term that I wanted to introduce, and that's a random variable. Okay? The random variable is the way we refer to an event. Okay? So you can have either discrete random variables, and if it's a coin toss, there's two random variables, tails or heads. And those are random variables for a coin toss. So that's for a coin toss. And these are random variables, RVs. I should talk something about it. But anyway, for a die toss, random variables are 1, 2, 3, 4, 5, and 6. For a success or failure task in performing a task. So let's call this human error. And you can call that success or failure, or else you can call it 1 or 0. Doesn't matter, but it's still a random variable. And it's just the way you name it. And so on. I mean, those are just some simple examples. But a random variable is the name that you apply to the outcome. Okay? And it's not just a single coin toss. This is an example. If I have 3 consecutive coin tosses, the random variable is the number, either the number of heads after 3 consecutive coin tosses, or the number of tails after 3 consecutive coin tosses. Doesn't matter which way I define it. But I can toss a coin 3 times, and I will either get 0 heads, 1 head, 2 heads, or 3 heads. okay, in those 3 successive coin tosses. Those are the possible outcomes. I already talked about discrete versus continuous, but something like a coin toss, or a die toss, or a shuttle launch, for example, or human error, are discrete. They're discrete because of the fact that it's either a success or a failure, a crash or a safe landing, and there's nothing in between. And for a die toss, it's either 1, 2, 3, 4, 5, or 6. There's nothing in between. You can't get a 1.5. Coin toss, it's either a tail or a head. You can't get anything other than that. Those are discrete. For a continuous, let's talk about the normal distribution. If I'm looking at heights, as long as I have enough resolution, there is an infinite number of heights that I can measure. If I have a stadiometer measures your height within less than a millimeter. It's an extremely accurate height measurement device. I still can get virtually infinite number of heights. They're not discrete, they're continuous across the entire range of heights. Inter-arrival times. Those 2 distributions that I talked about, the normal and the exponential, inter-arrival times. As long as I have enough resolution, I can get an infinite number of arrival times. There will be no set values for it. So those are examples of continuous distributions, when you have an infinite number of arrival times or infinite number of variability, infinite amount of variability. It's not restricted to discrete values, like a coin toss, die toss, human error. For discrete functions, we have 2 types of functions: a probability mass function and a cumulative mass function. So, and for I just realized that I talked about 2 slides at once, sorry about that. But for a continuous function, you have probability distribution function, PDF, or a cumulative distribution function. And I'll talk about this in a minute. But whenever you have a distribution, you talk about it in terms of its a probability function, PDF or PMF, and its cumulative function, a CDF or CMF, depending on whether it's discrete or continuous. This is 3 successive coin tosses. Okay, let's take a look at that. 3 successive coin tosses. My random variable here happens to be the number of heads. Okay, so for 3 successive coin tosses, the probability of 0 heads, and that is tail, 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 is 1/8. Okay, we can do that by enumeration because we know that there's 2 to the 3rd possible outcomes. 2 times 2 is 4 times 2 is 8. Right? There's only one way we can get this. By enumeration, we can see that there's to get 1 head. There's 3 different ways to get 1 head, so that's 3 and 8. And we can get there's 3 different ways to get 2 heads, so that's 3 and 8. And there's only one way to get 3 heads. And if you add those out, that satisfies our requirement that all of our probabilities for random variables add up to 1. And like I said, I'm using this because this is very intuitive. You can do it by enumeration. You can see where the probabilities are derived from. That's for a discrete random variable. Or discrete random variables. That's a probability mass function, because I am interested in the probability that it is equal to each one of these random variables. The cumulative mass function then is everything up to 1. Okay? So everything up to 1 is just all tails, so that's 1/8. Everything up but not including 2 is 4/8, because it's 1/8 plus 3/8. Everything up to but not including 3 is 7/8, because it's 1/8 plus 3/8 is 3/8. And then everything up to and including 3 is 1, because that includes all of our possible combinations of 3 successive coin tosses. So a cumulative mass function simply means the probability of everything less than a given random variable value. And ultimately, if you include all the random variables, you will get the value of the cumulative mass function to be 1.
Can you repeat that, just what you said about it's the probability of everything for the cumulative mass function?
It's the probability of everything less than a value for the random variable. So for instance, everything less than 1 is 1/8. Everything less than 2 is 3/8 plus 1/8. Everything less than 3 is 3/8 plus 3/8 plus 1/8. And then everything less than or equal to 3 is 1. Does that help?
Yes.
So let's talk about our first and the simplest of all the distribution functions, and that is the Bernoulli distribution. The Bernoulli distribution is the simplest because it's a single event with 2 possible outcomes. So it's P and Q. The probability of a success is P, and the probability of failure is 1 minus P or Q. And that is the convention. P is success and Q is failure. There's nothing that says that it has to be that way, but it is. Every probability distribution has a mean and a variance associated with it. I'm going to give you those when most of the time. The mean for, or the expected value of x for the Bernoulli distribution is P. The variance is P times Q. And so it's the expected value of x is the mean, the variance of x is the variance, and it's P and P times Q. So what we were doing with 3 successive coin tosses was 3 successive Bernoulli trials, or 3 successive Bernoulli events. And again, we can state that in a slightly different way. The same experiment, but the probability of 0 heads is Q to the 3rd, because that's a failure. And we're interested in heads, so no heads is a failure, and that probability is 1/2. To the 3rd is 1/8, right? Probability of getting 1 head is, by definition, 1 head, which is a success, and 2 failures, which is a failure, and then there's 3 possible outcomes, and from that we get 3/8. Likewise, for a value of 2, which is 2 heads, there's 2 ways to get that, so it's P squared. One way to get tails, which is Q times 3, and likewise for the 3 successes. I'm leading up to something here, so bear with me. If we take those 3 successive Bernoulli trials and look at them in and believe me, this is what I'm leading to is the binomial distribution, is the development of it. This is 3 successive Bernoulli trials with a successive failure, because here I'm saying that the probability of success is 0.3. Right? We can do it by enumeration with a tree diagram like this, and we know that there's 8 possible outcomes, and this is a diagram of how to get to those 8 possible outcomes. I can branch to a P or to a Q. At each one of and at the second toss, I can have a P or a Q after a P, or a P or a Q after a Q. The third toss, if I ended up in this branch, I can get a P or a Q. If I ended up in this branch, I can get a P or a Q, and likewise. And 8 different possible outcomes there. If I go ahead and multiply each branch, I go 0.3 times 0.3, that's 0.09, times 0.3 is 0.027. I call that the path probability. And then I look at the components for P and Q. I had 3 P's and 0 Q's, so that's what the exponent would be. It's P to the 3rd, Q to the 0. Go to this path, P times Q. So I had 2 P's, 1 Q, and so those are my exponents, and the probability of that path is 0.063. Let's look at this path. 0.3 times 0.7, P times Q times P. I have 2 P's, 1 Q, So it's p squared, q to the first, same probability. And finally, this path, p times q, so it's 1p, 2 q's. So those are my exponents for p and q, and that's the probability. And remember, the probability of p is 0.7, probability of q is p is 0.3, probability of q is 0.7. So do the same thing for each one of the 8 possible paths, 8 possible outcomes over 3 successive trials, and you'll end up with a sum of 1. Now notice that I've color-coded this. Okay. What I color-coded it for was, this is blue, that's unique. P to the third, q to the 0. This one has no color, that's unique. P to the 0, q to the third. In other words, 3 successive failures, no successes. This is 3 successive successes, no failures. 0.027, 0.343. Okay. Now, if I have in the sequence 1 success and 2 failures, there's 3 different paths that will provide that with the same probability. This one, and this one, purple. And then in the kind of rose-colored, I have 2 successes, 1 failure. 3 different ways to achieve that, all the same probabilities. Okay. Does everybody see where I've gone so far with this? Okay. This is why the binomial distribution is so handy, because this is just 3 successive Bernoulli trials, and you can see how bulky this has become already, how bulky the thinking is. Now let's summarize that. Random variable, I define 3 as 3 successes. Okay, 2 successes, 1 success, 0 successes. Okay, the coefficients, I'll come back to the coefficients. I can either count them by enumeration, because there's one way to get 3 successes, one way to get 0 successes. There's 3 ways to get 2 successes, and 3 ways to get 1 success. Another way we can do that is by combinatorics. I'll come back to that in a minute. And these are my exponents, which I just took from the previous slide, and the path probabilities. Okay? Now these coefficients, if I look at for the random variable of 3, this is 3 objects taken 3 at a time. N equals 1. For a random variable of 2, 3 objects taken 2 at a time equals 3. For 1, 3 objects taken 1 at a time equals 3. 3 objects taken 0 at a time equals 1. That's where the combination part of the binomial distribution comes from. This is where the exponents, p to the x1 minus p to the n minus x, come from. And then if we take the coefficients times the path probability, we get the total probability of getting 3 successes, 2 successes, 1 success, 0 successes. That's the cumulative probabilities of each one of those, which add up to 1. Do you see how this is going towards the binomial theorem? Because the binomial theorem is probability of x equal to little x equals n objects taken x at a time, p to the x, 1 minus p to the n minus x. And that's our probability mass function for the binomial theorem. The cumulative mass function for the binomial theorem, all that says is that if we go from 0 up to some number of successes, all we have to do is add each one of those together. So if I want to say probability of 0 or 1 successes, then I would add these 2 probabilities together. For the mean for the binomial theorem is n times p, and the variance is n times p times q. You can see the relationship to the Bernoulli event, because a binomial theorem or a binomial distribution is subsequent, at least 2 subsequent Bernoulli trials. taken in sequence. Well, let's take a look at a couple of examples, and I think that probably I should wait till next week to go on to the Poisson distribution. Now, give you a little bit of time to think about it. Okay. As this was so diplomatically pointed out to me last semester, since the probability of crashing the next shuttle mission is 0 because there are no more shuttle missions. Well, let's assume that there are, all right, for the sake of me. So up until it stopped, I believe this was a total of 135 missions. I think I looked at that a few years ago, and 2 crashes. So that means that the probability of crash, if it were to continue, we could use the idea of 0.0148. There's a couple of other ways you can think about it. Up to the second crash, I was on the 113th mission, so we could use a slightly higher probability than a more conservative estimate. Up until the second crash, I was on the, that must be a typo. Oh, prior to the second crash, I'm sorry. Prior to the second crash, it was 1 in 112, and that gives us an even smaller probability, not very conservative there. And up to the first crash, which was on the 25th mission, that's 1 in 25. The Air Force estimate, when they started this, interestingly enough, was 1 in 35. So their estimate was a higher probability of crash than actually occurred throughout the course of the program, which I found very interesting. They thought it was going to be worse than it was when they started. But anyway, let's say that they're restarting up the shuttle, and they're going to run 10 more missions, and they want to know the probability of having a crash in the next 10 missions. Applying the binomial distribution using 2 in 135, this one up here, which is the final outcome until they discontinue the program of, oh no, I used, this doesn't agree. I don't know why I did that. Well, let's do up to the second crash on the 113th mission. I don't know why I did that. But anyway, in the next 10 trials, so this is our P, our probability of success, our probability of failure. But we could use that as success, because what we're doing is we're interested in the number of crashes, so we call that our P. Could do the opposite, but 0P is about 84%. We can calculate the probability of exactly 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 crashes. And it gets diminishingly small once you get beyond 1. Okay, that's 1%. Once you get beyond 2. 1% is not diminishingly small. 15% is not great. But then once we get beyond that, it's very small probability, greater than 2 in the next 10. If I were to ask what's the probability of getting at least 2 crashes, probability of having at least 2 crashes, that would be an example of the cumulative mass function for the binomial distribution. And what you would do, getting at least 2 crashes, you would add up 2 through 10, or add up these 2 and subtract it from 1, right? Using the complementary rule. Okay, we're getting a sense of saturation, so why don't we knock off for today? Does anybody have any questions before you go? Yes.
On that previous slide, the more missions you have that are successful, does that change the probability of a successful mission? Like, let's say mission 136 with still 2 failures, 137, 2 failures. It's obviously, making a probability of a failure.
That's right. It gives you a better chance of having more successful missions.
The more you have, right?
That's right. Yeah.
And so in your events, 0 through 10, you're using a constant probability.
Yes.
And that's okay.
It is, because what we're doing is we're assuming, because what you would do with something like this is use such a large number that you consider it constant.
Oh, right, okay.
Yeah. This would be a an evolving number probably. And that's what I'm trying to illustrate here. As you can see, it would make a considerable difference depending on how you calculate P. And you probably would do that, but if I'm starting out and I'm saying, we're planning on doing 10 missions, what's my likelihood? What's my probability? This would be a good answer. After the next 5 missions, this probably isn't a good answer anymore.
Okay.
Yeah. Other questions? Why don't you take a look, rather than letting this percolate for 2 weeks, let's take a look at the first practice problem set. You could do 1, you could do 2, you could do 3, you could do 4, and you can do A and B of 5. That's about that. So we'll do 1, 2, 3, 4, and 5 A and B. And we'll start out by going over those to consolidate what we talked about this week. Okay?
Do we not have class next week?
No, we do. What?
You just said 2 weeks.
No, what I meant is rather than waiting 2 weeks to go over any of the homework, I wanted to consolidate with what you learned today, what I talked about today. Let's put it that way.
What homework problems would we be able to do?
1, 2, 3, 4, 5, 8.
Well, these are practice problems.
Oh. Ah. Never mind.
You good?
I'm good. I'm sorry?
I wasn't gonna show up next week.
You can do 1, 2, 3, 4, 5, 6, A, and B. All the way up to 6A and B. Apparently it was longer 3 weeks than I thought it was. That's more like it. Okay? Well, I will see you next week.